Hi everybody. We're going to use some super cool technology today to go through the mechanism of a serine protease. And these are one of two mechanisms that we'll do. In this particular case, we focus on the serine mechanism because it's named after the residues that sit in the active site that carry out catalysis of bond breakage on a peptide bond. Okay, so why is it a serine protease? Well, what you can see is you look here and there's a serine residue, and that's what the name is due to, because that serine will play a very important role in the catalytic mechanism. However, the serine is supported by the two other residues in what we call a catalytic triad. One is a histidine, and the other one is an aspartic acid. Okay? And those three residues will work together to help change the chemistry that surrounds the peptide bond that's targeted for proteolysis in order to carry out bond cleavage. So let's take a look at how that mechanism proceeds, and we'll do this in a couple of different phases so you can see what each step is. As we're going through this, remember, we've talked a little bit about burst kinetics, and you're going to think about like the fast step versus the slow step and how that relates to the phases that we described. Okay? So when a peptide, hapless peptide, drifts its way into this active site, what it finds is the catalytic triad is set up, ready to attack it. Okay? And what happens is that initially the peptide drifts in, and there's a little bit of an interaction here between this oxygen and this carbonyl carbon. And that's facilitated because of something that happens very rapidly, that the electrons that are on this nitrogen in the histidine ring can attack this proton and pull it off of the serine side chain, the serine side chain oxygen. Okay? And when that happens, a couple of things ensue. So first of all, the proton gets abstracted onto that nitrogen. These electrons collapse into a bond and form an actual covalent bond between the oxygen and the I'll draw it nicely there, and the carbonyl carbon. That, of course, forces the electrons to redistribute out of this pi bond here so that it's now going to form something a little bit different. So let's move over here, some cleaner space, and we'll look at what happens next. So, like I said, you get, first of all, this redistribution of electrons, so that now what you have is what's called an oxyanion. Okay? And that oxyanion is stabilized by a couple of protons from a glycine and a serine. These are actually side chain in the backbone of the protein, protons that are part of that, and they are forming what we call an oxyanion hole. And that's just a position in the enzyme. Or think about the three-dimensional structure of an enzyme. It's a position that's there that's stabilizing the formation of an oxyanion, right? And that's important for the kinetics of the enzymatic reaction. So also remember that we now have a new covalent bond here between the carbon that's associated with the peptide bond, and that we now have a proton and a positive charge on this nitrogen. Okay? So that's the resolution of that first step. And now what we look at is this scenario is fairly stable, but it's not perfect because you've got positive and negative charge in close apposition to each other within the active site. And what you have is this pair of electrons on the nitrogen that's in the peptide bond. Those are very going to rapidly go after this proton. So you think about like this proton's making its way around the entire mechanism. They'll pull that proton off of the histidine. And when that happens, these electrons can collapse back into the ring. Okay? And so what is that going to leave us with? If this proton is now moving, let's just erase this so we can restructure what's happening here. Now what you have is something that looks like this, right? This is kind of back to normal. And now you have a positive charge on this nitrogen. While this whole thing was taking place, there's one very important part that is happening kind of in the background that's important to focus our attention on. And that happens to involve the role of the aspartic acid. The aspartic acid is there to kind of hold the histidine in place and control its action. And part of that is through the formation of a low barrier hydrogen bond. So the proton on the histidine ring is hydrogen bonded to the aspartic acid carboxylic oxygen. But when it undergoes this intermediate step, one can form a low barrier hydrogen bond. And that just is a unique sort of positioning of a proton where it's shared between these two atoms on two different side chains, okay? And that's an important part of stabilizing this step of the reaction, okay? Once the bond is broken here and this proton is moved, that low barrier hydrogen bond itself can go away and reset itself. So we can just get rid of these. And what you see is a scenario where this is a Zwitter ion across that peptide bond, and that can collapse. So these electrons can collapse here to reform a pi bond, and that can break the peptide bond, and the electrons can move in here. Okay? And when that happens, you end up with the next phase of the reaction. So you can imagine what we have right here is a collapse around here. I'm going to get rid of these so you guys can see a little bit better. We'll take out the glycine and the serine. Whoops. And let's take out these red arrows. Clean that up a little bit so that we can do the key thing, which is to remove that peptide bond. So once that whole thing collapses, you reform this double bond, and now you have NH2 at the end of a new C terminus of a protein. So that that peptide bond has been broken, right? So this is the key step where the peptide bond is broken down. And once that happens, you have the first product is formed. And so think back to burst kinetics and the way that the first product is formed fairly quickly and can dissociate and leave the enzyme active site. But we're not finished because we have to move on to the second phase of the enzyme. Remember, an enzyme has to be reset so that it can go through multiple cycles of enzymatic catalysis. And if you look here, what you see is this enzyme is not reset. It's still covalently bounded to the carbon that was involved in that peptide bond that's just been broken. So we're going to now move on to the second step, which is essentially resetting the enzyme for a next round of catalysis.